Hello. This looks pretty dark. It's not a shady thing, but I want to show you something on my whiteboard, and this is probably the best way to do it. When we end up getting our pendulum data for time versus length, we're probably going to have a question as to whether the relationship between time versus length is a direct relationship or whether it's a power function. Now, if you remember back from the graphical method summary I asked you to tape in front of your composition books, which is a small blue sheet of paper, and it looks like this. There are several different types of relationships which we have. And normally what we do is we think that the one that fits the reality of the world around us is the one that has the closest fit to a particular shape. Oftentimes it could be a direct relationship or a linear function. We found with some of the pendulum relationships there was no relationship. And then we have things like an inverse relationship, an exponential relationship, and what's called a power function or quadratic relationship. So we're choosing between this and this for time versus length. So I've already imported some data into from a graphical analysis. And so if you take a look at this, okay, so that's right here. Hey, there I am. So this is the raw data. Now notice I've scaled from 0 because if I don't scale from 0, all I get is something that looks like a weird straight line. And in context, we know that zooming in on data can misrepresent it. So when I look at this, it looks like it might be curving down towards 0 like a power function, or it might be a straight line. The way to help you determine this is to try a curve fit. So if I apply a curve fit, and it always does linear at first, and I apply that, I end up getting what looks like a pretty good line, but it's a little odd that the y-intercept is here around 0.6, 0.7 seconds. And the reason that should seem a little odd is as your pendulum lengths get shorter and shorter, we know that the time gets shorter and shorter, but it seems like odd that in nature we would just have a random time for a y-intercept. It seems like it should either go straight across or tail down towards 0. The other thing is, if we collect very short lengths for pendulums, we actually can get the time significantly shorter than this. Now, these were the limits that we had in the lab that Pivot Interactives gave us. Went from around 26 centimeters was the shortest, somewhere around 70 centimeters was around the longest. So, unfortunately, it's a pretty narrow range of data. And anytime you have a narrow range of data, something that is really a curve can look like a straight line. So, one thing we look at is down here, and it's called an RMSE, and I'm going to sneeze. Bless me. This RMSE stands for root mean square error. My watch is making a weird reflection. That's kind of fun. And this is 0.0201. That's pretty good, and you can see the dots are pretty close. But if we can find a relationship with less than that square error, root mean square error, it says it's a better relationship. So I'm going to try the power function, and down here, apply curve fit, power, and apply. And now if we look at that, that root mean square error is 0.0027. So that's much lower, almost 10 times lower than what we had before. And this looks like the dots have got a better fit, and it also tails down towards 0, which kind of makes sense if we get a shorter and shorter pendulum length. It's going to go from slow to fast. So now here's the thing. We're going to go outside and make a prediction about a challenge pendulum out by the football stadium. And the problem is if we want to do this and make an accurate prediction, it's really hard to do that for a curved line. So if we time something, and then we time it at, say, 4 or 5 seconds, we can tell that this is flattening out, but exactly how flat it gets can get really difficult. So one thing that can be very helpful to us is to linearize what looks like a curvy graph. How to linearize it is actually stated, this isn't going to get in here, on this blue sheet also. The rightmost column, or the middle column where it says modification to linearize, for a power function says y squared versus x. So what that means in terms of log or graphical analysis is instead of having time per swing, I need to have time squared per swing. So I'm going to get rid of this. And what I'm going to do is I'm going to make a new calculated column. And when I do that, it says add calculated column. What I can do is I can say time squared. Now the units would be second squared. I've got to use the caret function because there's nothing up there to do that. And insert expression. Well, this looks kind of complicated. But realizing all I need to do is have y squared. That's all I've got to do. So in this case, I look at that and I don't see a y squared. But I do see, or to a power, I do see this, and a and b are just constants. So if I don't see anything with y in there, I'm going to go and choose this. Just make sure that I square that variable. So I'm going to do that. So the parameter a is just going to be 1. Here, this parameter, I'm going to put in 2 because I want to square it. I'm going to apply that. So now what I've done is I've made a column, a new calculated column called time squared. I actually did this earlier, so because I want to make sure that it worked. So when I look at that, now over here I've got time squared, and that looks like a super straight line. And in fact, now when I apply the curve fit and I do linear, it gets me a much nicer fit than I had before, and it goes right towards 0, 0. So I can use a straight line to make a prediction really easily. So for example, if I have something where we're outside by the football stadium and I have a time per pendulum swing that is 4 seconds. Well, this is time squared. So I would square 4 seconds and get 16. And wherever 16 is, where this line would match up down here with the length would allow me to predict the length of that. And that allows me to predict something, first of all, with a weird relationship, and second of all, that could be way outside the boundary of the data that I collected. So I think that's really interesting. Now, when you do something like this, it helps to have really good data to begin with. So in this case, then, I would save this. Now, the other thing you can actually do is you could show what would happen if we plotted both of these on here. So I'm going to get rid of this linear function, but if you notice my original data, now it shows up really easily as being curved, and the new data, which is in red dots up here, shows really easily as being straight line. And again, much easier to make a prediction off of a straight line than a curve. So that's both how we linearize a graph and why we linearize a graph. And my goal is for you to do that with the data that your group collects or your class collects for the pendulum time versus length, to import that into graphical analysis, square the time that you get for that, and come up with an equation. For this equation, the way I would do that, so if I now make this linear curve fit and apply, I start out with that, but remember, I'm not looking at y's and x's, I'm looking at time squared and length. So I would say time squared, my equation would be time squared is equal to the slope, which is 0.0406, and that's going to be seconds squared per centimeter, multiplied by the length. And my y-intercept is negative 0.0096. That's small enough where we can ignore it. If our y-intercept is something we think is 0, and it's less than 5% of our maximum value, which is up here around 2.5, then we can decide that that's 0. That's a pretty reasonable assumption. And that's just a sort of a guided way to do that. If you want to leave it there as something non-zero, you absolutely could do that. So like I said, now, if I get a time outside and I square it, I divide it by 0.0406, it will allow me to predict the length of that challenged pendulum outside. So hopefully we can come up with some pretty good predictions, and then that'll bring this whole lab together. Thanks.